Chapter 13 Log Likelihood and Optimization. In this chapter, we will look more closely at the optimization process by which the logistic regression model finds the optimal parameters. In the optimization of logistic regression models, it is more common to use the log likelihood function than the likelihood function. Taking the logarithm allows the product of the likelihoods to be converted to a sum, which simplifies the computation. Taking the logarithm also improves numerical stability and allows the optimization algorithm to work more efficiently. Finding the parameters that maximize this log likelihood function is the goal of training a logistic regression model. As we saw earlier, the likelihood function can be expressed by this equation. Applying the natural logarithm to this equation, the logarithm of the product becomes the sum of the logarithms of each term by the law of logarithms. Further, applying the law of logarithms moves the exponential part to the front of the logarithm. In this way, the computation of the likelihood function is simplified from a chain of products to a sum. This simplification facilitates differentiation and makes it easier to apply optimization algorithms such as gradient descent. Optimization is a minimization problem of finding the parameter values that minimize the loss function. The loss function is a function used to quantify how much a machine learning model's predictions deviate from the observed data. When we train a machine learning model, especially a supervised learning one, the goal is to minimize the value of the loss function. The smaller the value of the loss function, the closer the model's predictions are to the observed data, meaning that the model performs better. There are various types of loss functions. We need to select the appropriate one depending on the type of the model and problem such as regression, classification, etc. The loss function plays three roles in the model learning process. The first role is as a performance indicator. The value of the loss function serves as an indicator to assess the current performance of the model. The smaller the value, the better the model's performance. The second role is as an optimization goal. Minimizing the loss function is the main goal in the model training. Optimization techniques such as gradient descent are used to calibrate the parameters toward this goal. The third role is to provide feedback. Changes in the value of the loss function during training provide feedback on whether the model is moving in the right direction or needs calibration. In a logistic regression model, the log likelihood must be maximized to find the optimal values of the parameters. However, since optimization is generally treated as a minimization problem, the negative log likelihood is used as the loss function in logistic regression. Thus, maximizing the log likelihood and minimizing the loss function pursue the same goal. The negative log likelihood is also called the cross-entropy loss in the context of machine learning, especially in classification problems. Mathematical optimization methods such as gradient descent and Newton's method are used to find optimal parameters in logistic regression. These methods find the optimal parameters by iteratively calculating and updating the parameter values that maximize the log likelihood function. The gradient descent method calculates the gradient of the log likelihood function for a parameter and uses it to update the parameter. The Newton's method uses the Hess matrix for faster convergence. This chapter covers the gradient descent method. The gradient descent method is an optimization algorithm for finding the minimum of a function. The gradient descent method finds the minimum of a function by gradually updating the parameters along the gradient of the function. The parameter update at each step is done by subtracting an amount proportional to the gradient from the current parameter. This process is repeated as the function approaches its minimum value. Then, the point at which the gradient becomes zero is the minimum or maximum value of the function. As mentioned earlier, in the optimization of a logistic regression model, maximizing the log likelihood function is synonymous with minimizing the loss function. Let us outline the mathematical procedure for maximizing the log likelihood function using the gradient descent method. Step 1 is to compute the gradient. In this step, we compute the partial derivatives of the log likelihood function with respect to the parameters of the model. This yields a gradient for each parameter. The gradient identified here is the direction in which the log likelihood function shows the steepest increase. The next step is to update the parameters. In this step, the gradient obtained in step 1 is multiplied by the learning rate and subtracted from the current parameters. Here, we are aiming to maximize the log likelihood function, so we add. But in a normal optimization problem, we would subtract from the parameters. This gradually updates the parameters toward their optimal values. The third step is to determine convergence. Step 1 and 2 are repeated until the parameter updates become small enough, or the increase in the log likelihood function becomes small enough. Through this process, we can determine the value of the parameter at which the log likelihood function is maximized. Let's look at the gradient descent process in more detail. Before computing the gradient, we need to set the parameter's initial values. If the parameters are beta 0 and beta 1, then we need to set the appropriate initial values for these beta 0 and beta 1. These initial values will be set to 0 or some other random value. The next step is to compute the gradient. Initially, the gradient of the log likelihood function is computed using the values of the initial parameters. That is, we calculate the value of the partial derivative of the log likelihood function. This gradient indicates how changing the parameters will increase the log likelihood. When the parameters are updated in step 3, and then we come back to step 2, we compute the gradient using the updated parameter values. The parameters are then updated using the computed gradient and the learning rate. The learning rate is a small positive value that is preset. The update equation looks like this. If the partial derivative of the log likelihood function is positive, this means that the gradient of the log likelihood function is positive at that point. This implies that increasing the value of the current parameter may increase the log likelihood. In other words, increasing the value of that parameter is expected to improve the fit of the model and move in the direction of maximizing the log likelihood function. Conversely, if the partial derivative is negative, the log likelihood is decreasing with the value of that parameter because the gradient is negative. In this case, decreasing the value of the parameter will increase the log likelihood and move toward a better model fit. If the partial derivative is 0, the gradient is also 0, and the log likelihood function may have reached the local minimum at that parameter value. Other conditions, such as the sign of the second derivative, must also be considered here to ensure that the log likelihood function is at its maximum value. In the gradient descent method, parameter values are iteratively updated to find the combination of parameters that maximizes the log likelihood function. The learning rate is used to adjust the amount of the parameter updating during this update process. In the fourth step, determining convergence, we observe whether the learning process is approaching its end. Convergence in here refers to the state in which the value of the loss function does not improve significantly any further, or, to put it another way, the parameters have stabilized to their optimal values through a process of repeated updates. This step is therefore the step to evaluate whether the algorithm is approaching the optimal solution. Specifically, criteria for stopping the model training process are defined, and step 2 and step 3 are repeated until the criteria are met. Model training is terminated when the criteria are met. The criteria used here include the following: the preset maximum number of iterations. The amount of parameter update has become small. The change in the value of the loss function has become less than a certain level. And the magnitude of the gradient has become sufficiently small. The number of iterations is the number of iterations between step 2 and 3. The appropriate number of iterations depends on the complexity of the problem, the size of the data, and other factors. A general rule of thumb is that several hundred to several thousand iterations are often required. In practice, the decrease of loss function value is the main indicator of convergence. The learning rate is used to adjust the amount of parameter updates during the parameter update process. The appropriate learning rate depends on the problem and must be determined experimentally. Typically, one starts with a value such as 0.01 or 0.001 and adjusts it while observing the behavior of the loss function. If the learning rate is too high, the loss function may overshoot the minimum value and diverge without finding the optimal value. This is a condition where the parameter update steps are too large and go too far down the valley of the loss function. On the contrary, if the learning rate is too low, the parameter updates will be very small, requiring a very large number of iterations to reach the optimal value. This leads to a very slow learning process and large computational costs. As we saw above, in the gradient descent process, the gradient calculation in step 2 computes the partial derivative of the log likelihood function. Let's take a look at the process of computing the partial derivative of the log likelihood function. The log likelihood function is represented by this equation, where pi is the logistic function, probability that y equals 1 at the ith data point. To perform the partial differentiation of the log likelihood with respect to beta 0, we can apply the chain rule. The outer function is the logarithmic function, and the inner function is pi. First, the derivative of the logarithmic function, which is the outer function. The derivative of the logarithmic function is this fraction. Thus, by applying the derivative of the logarithmic function, we can transform the equation in this way. Next, we differentiate the inner function, pi, with respect to beta 0. Let's look at the inner function, pi. Pi can be rewritten in this way. It is a composite function that has these functions as the outer and inner functions. Using the chain rule, we find the derivative of pi as a product of the outer derivative and the inner derivative. The derivative of the outer function x to the power of -1 is minus x to the power of -2. According to the derivative rule for exponential functions, the derivative of the inner function takes the form of an exponential function with a minus and only the exponential part remaining. The expression for pi, the derivative of the outer function, and the inner function derivative are shown here. Using them, we will apply the chain rule to the partial derivative of pi. The negatives cancel out each other and simplify the equation. Furthermore, we transform it into fractional form. Continue from the partial derivative of pi in fractional form. Add 1 to the beginning of the numerator and subtract 1 from the end. This operation does not change the numerator value. But this operation allows one fraction to be decomposed into subtraction between fractions. The left-hand side can be reduced, and the right-hand side can be expressed in the form of a square. Here, from the definition of pi, we see that both sides can be expressed using pi. By substituting pi, we can simplify this equation in this way. We have obtained the derivative of pi with respect to beta 0. We now return to the expression for the partial derivative of the log likelihood function. Substitute the partial derivative of pi. We can simplify the equation by canceling out each other, the pi's on the left side and the 1 minus pi's on the right side. Then, let's remove the parentheses and expand. The final expression is the simple expression. In this way, the partial derivative of the log likelihood function can be expressed by a simple equation. When differentiating a function, we usually differentiate by the variable, not by the coefficient. However, in the above, the log likelihood function is differentiated by the parameter as a coefficient, not by the input variable x. Why? The reason is the difference in purposes. The reason for differentiating a general function with x is to explore the behavior of the function as a function of x. On the other hand, in the likelihood function, the objective is to determine the optimal values of the parameters based on the observed data, which is known. Therefore, it is differentiated by the parameters, not the variables. In other words, in maximizing the likelihood function in optimization, x, the input value of the likelihood function, is known, but the intercept beta 0 and coefficient beta 1 are unknown. So, in the partial differentiation of the likelihood function for optimization, x is rather positioned as a constant, and the intercept beta 0 and coefficient beta 1 as variables. As we have seen, log likelihood functions instead of likelihood functions are used in logistic regression optimization. The use of log likelihood function has several advantages. First, the logarithmic function varies more slowly than the exponential function, preventing the values from becoming extremely large or small. If a value becomes too large or small, it exceeds the range of values that can be computed by a computer. This advantage allows optimization algorithms such as gradient descent to approach the optimal value in small steps. Second, The logarithmic function also makes it easier to compute the gradient during the optimization process, because the derivatives of the natural logarithms are simple fractions. Moreover, since the log likelihood function is always a concave function and convex on top, the local maximum is the overall maximum. Because of this feature, it is easier for the optimization algorithms to find the overall maximum.